Hi, Space Village. Today we'll be talking about space orbits, and I'll bring here the disclaimer. This is my review on the Florida Tech course on space technology. Disclaimer is on. Yeah, all omissions are my own fault, but I made some investigation and research about this, and I'm bringing more examples on space orbits that are really fundamental for a lot of the definition on what, for example, a satellite will utilize um, to bring information back to Earth or from Earth and onwards. So this video is very Earth-centric. The concepts can be applied further ahead as we move to the Moon and Mars and other celestial bodies. Okay, given enough injection velocity objects fall around the Earth, explode that elliptical trajectory. But we do need that enough speed around the Earth to stay in a stable orbit, mostly because the Earth atmosphere expands, and for example, it's too hot, okay? So imagine like a balloon, when you see the balloon expand when it's too hot. So the same thing happens. If the satellite is in a fixed point, let's say that is over here, it's in a fixed point, I'm gonna call the Earth atmosphere picks him up. So the higher the velocity, the velocity, more energy, and then even a bigger orbit. Meaning that I need to move quicker in order to maintain that high level of the relation to the Earth. Above the atmosphere, where there is almost no drag, objects do not slow down quickly. So you need to have some thrusters, something that makes the object stop. And inclination, it's the relationship to the equator. I'll give you examples of all of these. That's what I felt that was needed. Pretty cool thing in here. So low Earth orbit, it's that circle around the Earth, 180 to 2,000 kilometers, pretty big, isn't it? Then mid-Earth orbit, 2,000 to 35,000, and then high Earth orbit and geosynchronous. Essentially, think about that the Earth is moving, at the same time the satellite is moving. And then you do have lunar orbit. That's pretty cool, pretty far away. One way of classifying orbits by altitude. So the excellent illustrations by Robert Simon. Let me play you a video that I found really useful to. This one is from a geosynchronous orbit. So in red, that's where the satellite is moving on, and from the same source. Pretty cool, correct? So you can see that the satellite is always passing by the same, although the Earth is moving and the Earth moves around the sun, not in reverse, okay? We know that for science, this is amazing because you can always be watching, well, the satellite is, let me stop the satellite. Go satellite, back. Okay, stopping the satellite in here, boom. So as the Earth rotates around the sun, you kind of get always the same angle, and the satellite can receive images in here and compare this for science. An important thing. So that was one cool video in there to show how this really works. And as we get back, so that another example as we move ahead is having these three different orbits. Sun synchronous, so something around the one that I've just showed the example. Then GPS moves around here and there. You'll see more satellites in there to make the coverage, and geostationary. And we do have the indication of the speeds that are taken by the red markers. Again, excellent animation by Robert Simmon. Let me show you the example with the orbital periods. And then this is a really cool example because, okay, I want to bring your attention to, this is really a quick video. Pause. Okay, see the one on the top in here? And if we focus on a specific spot on Earth, it will be you will be trailing or moving at the same at the same time. So it's like I'm always watching the same thing. The same thing is over there. Okay, I'm all, like this. If the Earth is over here, I'm always watching the same direction. Pretty cool to see that happening. It's and you see the different speeds. The one that is more near the Earth moves much more quicker. Okay, in order to maintain that orbit. Pretty nice, isn't it? I also thought. Um, Now, moving ahead, it's important, more stuff. Okay. And this is really something that is different. Uh, Another way to characterize the orbit is if it is a perfect circle, the eccentricity, that is the variation on the wobbliness, okay, it's the E. I should have the equation around in here, but as more as you move away from that perfect circle into more of this elliptical size, E becomes zero point 0.9. So think of this as the distance to the axis of the center of a circle. One of the most interesting orbits, it's called Monomolia, and I do have a great video, man, that can explain how this works. There are many of them, but this one is probably one of the best that shows. There we go. Really interesting. Okay. See the Iridium constellation over there, lower orbit. And yes, this is what's happening. It's our satellite in here is really getting close to the Earth, and now moving out. You felt the breeze, correct? Amazing work in here, created by Arki Marimi for Dr. Azam Arasta. Um, I just now you can see that you are watching a specific region on Earth. Pretty nice. Here we go. Back to the spin. Okay, see the focus on that specific region. Going down for a run. Okay, that was it. So great work from the Rocketeer. Okay, over there. Okay, another important thing is the orbital inclination is the angle between the plane and an orbit of the equator. Um, we've seen the video already, so I think we can move this on. But it's this inclination over here that allows you to, for the satellite. Of course, Earth moves, okay, and it's not flat. Given if, so summary, given if enough injection and velocity and velocity objects fall, we've seen after we move outside of gravity pull, we need to maintain a certain speed in order to stay in a stable orbit, or if not, you're going to be dragged down. That effect it changes over time. With higher velocity, you do have more energy. You go into a bigger orbit. You need to check that. What does it mean, bigger orbit? Because in this case, you maintain the same orbit. Above the atmosphere, where there is almost no drag, objects do not slow down quickly. So we need to get some pull. An important thing, if you want to do that, is to, on Earth, if you want to move faster, you move, you pull, you go in this direction. In fact, on in space, if you want to move slower, you need to push your satellite. You need to push the direction of the strength in the direction of the Earth, so that your satellite moves outside of the Earth gravity pull. So it's a bit of a strange maneuver that we need to do. And the inclination is the relationship to the equator. Okay, want to know more about space? Subscribe to my YouTube channel. It's called Got Space Processes, Entrepreneurship, Technology, and How to Become an Astronaut. And it's over here. It's called Epic Space. Continue the reviews. Enjoy your day.